Okay, thanks for the introduction. I would like to start with a short summary of the population receptive field mapping method in the visual cortex, which was introduced about 10 years ago by Dumoulin and Vandel. And as you know, most of the visual system shows a retinotopic property, and with retinotopic mapping we try to visualize how the position in the visual field and the region in the visual cortex correspond using retinotopic maps. So we therefore present a visual stimulus like this flickering bar to the subjects lying inside the scanner, and it's just important that the different visual field positions experience a unique time course with regard to visual stimulation. And we can then define a receptive field, a population receptive field, which is shown here in blue. And this has various parameters. So, for example, the eccentricity and the polar angle, which define the position of the PRF, and also it has a certain size. And with this information and information about the stimulus you see here in red, we can model the expected bold response, which you can see below. And of course, we also record data using fMRI from the different voxels in the visual cortex, and we then try to optimize our PRF parameters so the model fits the measured time series best. So if we do this now for every voxel, we can create retinotopic field maps, like I show you here with the eccentricity parameter. And as I already mentioned, we also need more parameters to uniquely define PRF, which is, for example, the polar angle and also the PRF size. And the nice thing about the polar angle is that we can use it to also delineate different visual cortex regions, because phase reversals happen at their borders. So we did a few studies on 3 Tesla, for example. This one where we tried to estimate artificial scotoma size in healthy subjects. So we have slightly modified the presented stimulus here by defining central regions, circular areas, where we didn't show the flickering bar, not the visual stimulus, and therefore simulated the scotoma. And here are the results. On the top you see again the retinotopic map overlaid on the white matter mesh. And at the bottom there is a coverage map, which can be created by just plotting the estimated PRFs of each subrothreshold voxel back onto the visual field. And looking at the results for the artificial scotomata runs, we can see the effects of these scotomata both on the retinotopic maps and in the coverage map for scotoma down to a size of 1 to 2 degrees visual angle. So we also performed these experiments in patients which are suffering from real central scotoma. For example, here, exemplary a Stargardt's disease patient, and the interesting thing here is that he is still a foveal sparing in the center, so he's still able to fixate quite stable, which is very important for high quality retinotopic maps. And the black area below is the result from microperimetry, which is the gold standard for detecting visual field defects. And here we have the result from our PRF mapping using fMRI, and we see that we also can detect very nicely this ring-shaped scotoma. So unfortunately, not every patient is able to fixate this stably, which is why we also did a study using an eye tracker inside the MRI. And you can see here that we not only recorded the eye tracker data to confirm stable fixation, but we also used this data to correct for some errors which were due to unstable gaze fixation. So although this data already looks quite nice, there are still problems where the model doesn't manage to explain the signal correctly, and there are inconsistencies therefore in the retinotopic maps. And this could be due to partial volume effects and also segmentation errors. And one way to improve this would be higher spatial resolution, which of course would come with decreased SNR, which is the reason why we decided to move to ultra-high field, which in turn then increases the SNR. So our question was now, if we reduce the voxel size to half the volume, so going from 1 millimeter resolution, which we already used at 3 Tesla, to 0.8 millimeter resolution, is the SNR still sufficient to obtain reliable results? And is the automatic segmentation precision high enough to allow for unsmoothed retinotopic maps? So we measured 10 subjects on a 7 Tesla scanner. We also recorded a T1 weighted MP-RAGE image with a resolution of 0.7 millimeters isotropic, and this was then used for segmentation of the white and the gray matter. Further analysis was then just performed on the gray matter voxels. So for the functional measurement, we used the CMRR multiband sequence with a repetition time of 1 second, multiband factor of 2, and each run was about 5 minutes long. So, and as I already said, we did these experiments with a resolution of 1 millimeter and also with 0.8 millimeter with a slightly higher grapper factor. So we, of course, have a very nice contrast because of the high resolution and 7 Tesla anatomic map, but we also have to correct for distortions to get a nice segmentation, which is why we recorded field maps using the Aspire method, published recently by Eckstein et al., to perform unwarping on the EPI images, enhance segmentation, and therefore also enhance our retinotopic maps. So this is the result of 4 concatenated runs for the 1 millimeter sequence. So this are about 20 minutes scan time. And keep in mind that both the overlaid map here on the cortex and the underlying data is unsmooth. And next is the 0.8 millimeter isotropic result, which also shows a very nice map and a very smooth transition from central to more peripheral areas, even though the underlying data is unsmoothed, and even in some areas also shows a more a better fit of the model. So looking at the coverage maps again, here for the 1 millimeter resolution and here for the 0.8 millimeter resolution, we can see that both are quite homogeneous, but there are also some areas where maybe the high resolution map manages to or has a higher PRF center density and therefore a better coverage. And the question we had now was if it's also enough to just measure one run, if we get a really nice PRF map, also with a scan time of only 5 minutes. And it seems this is the case. This is the result for a 0.8 millimeter run, just a single run measured in 5 minutes. And the unsmooth maps also look quite smooth and good. And on the right, you also have the polar angle map, which easily allows us to delineate the different visual cortex area, in this case, the primary visual cortex. So we then looked at the stability, which is, of course, very important for these unsmooth runs. And we did this by comparing the estimated PRF center position and calculating the distance of each voxel over runs. And we ended up with a result of 0.7 degrees visual angle for a total of 14 degrees visual angle, which were stimulated by our bar stimulus. So it's a pretty stable result. And I also want to hint at our second poster where we compare different retinotopic stimuli. This is interesting because different stimuli sample the visual field in a different way and maybe have advantages in certain areas of the visual field. And we had now the question if we can combine these advantages of the different stimuli. And we introduced a classic combined wedge and ring stimulus additionally to the bar stimulus. And if we now look at the averaged coverage map over 9 subjects, we see that both the 8-bar and the combined wedge and ring stimulus have some weaknesses in different areas concerning the coverage. And if we now combine these 2 runs on a voxel-by-voxel basis by picking the PRF model with the higher explained variance, we get this combined map, which shows a much more homogeneous coverage all around. So to conclude, unsmooth PRF maps can be estimated at 0.8 millimeter isotropic on 7T. This is possible with a single short 5.5-minute run. Also, the unsmooth maps show a high stability, even though the SNR has been reduced due to the higher resolution by halving the voxel size. And also the different returnotopic stimuli can be combined to improve both the visual field coverage and returnotopic maps. And finally, I would like to thank my team at the Medical University of Vienna and also our collaborators. Thank you for your attention.